There are four main kinematic equations, each of which can be derived from the simple expressions that velocity is equal to change in position over change in time, and that acceleration is equal to change in velocity over change in time. If we take a further look, that acceleration is the change in velocity over change in time. And we rearrange this to be acceleration times change in time equaling change in velocity. We can integrate each side of our equation. The left-hand side will be integrated from some time t to some initial time we will set to be 0. And the right-hand side can be integrated over some final velocity over some initial velocity. What I get is acceleration times time is equal to some final velocity minus some initial velocity. I can set this equal to the final velocity being the initial velocity plus acceleration times time, which gives me my first equation. If I now take a look at the fact that velocity is equal to some change in position over change in time, and I use this expression for final velocity that I've obtained from the first equation to be plugged in for this velocity here, what I get is some initial velocity plus acceleration times time is equal to some change in position over change in time. I can rearrange the equation to become some initial velocity plus acceleration times time times change in time is equal to some change in position. And if I integrate again, the left side being integrated from some final time t to some initial time 0, the right-hand side being integrated from some final position to some initial position, what I get is some initial velocity times time plus 1/2 the acceleration times time squared is equal to some final position minus some initial position. Now if I rearrange this to be equal to the final position, I get the initial position plus the initial velocity times time plus 1/2 acceleration times time squared, which gives me my second equation. My third equation is derived from using both expressions of velocity equaling change in position over change in time, and that acceleration is change in velocity over change in time. If I set both equations equal to my change in time, I get change in time is equal to change in position over velocity, and change in time is equal to change in velocity over acceleration. I can now set these two expressions equal to each other. So change in position over velocity is equal to change in velocity over acceleration. If I move them to their corresponding sides, I get acceleration times change in position equaling velocity times change in velocity. And I integrate the left-hand side being integrated from some final position to some initial position, the right-hand side being integrated from some final velocity over some initial velocity. I get acceleration times my final position minus initial position equaling 1/2 my velocity squared evaluated from the final velocity to the initial velocity, which is equal to 1/2 v final squared minus v initial squared. If I rearrange this and I rewrite x final minus x initial to be delta x, what I'm left with is my final velocity squared is equal to my initial velocity squared plus 2 times my acceleration times my change in position, giving me my third equation. My fourth equation is obtained from the first two equations. If I set the first equation, v final, which equals v initial plus acceleration times time, and I set this equal to acceleration, I get acceleration equals my final velocity minus my initial velocity, all divided by time. And I use this expression for acceleration to plug it into my second equation. So x final equals x initial plus v initial times time plus 1/2. Instead of writing acceleration, I'm going to write v final minus v initial over time times time squared. And if I do some simplification, I can get change in position equaling, and I'm going to write this as 2 over 2, my initial velocity times time, plus 1 over 2 final velocity times time, minus 1 over 2 initial velocity times time. I can simplify this further because parts of this initial velocity will cancel out to be change in position equals 1/2 initial velocity times time plus 1/2 final velocity times time. So my change in position equals 1/2 initial velocity plus final velocity times time, which gives me my fourth kinematic equation. And this is how you derive all 4 kinematic equations.